Okay, let me start our recitation, third recitation. Let me share the screen. Okay. Today we will solve the problems about continuity of the functions and also the product of the metric space, okay? Cartesian product of the metric spaces. Problem 1. Prove that the set of all sequences of real numbers which converge to 0 is a closed subset of this metric space with supermetric, I mean uniform convergence metric. So this is a bounded sequences in natural numbers, okay? In fact, bounded functions in natural numbers, we use the uniform convergence metric. So let's define the S. Our S is AN in okay. And such that AN goes to 0 as n goes to infinity. Okay, so how can I show that this S is closed? Okay, we call that guy. We will show that as the submetric is complete metric subspace of En D sub. We know that metric space is complete. And this will implies as in En is closed. Recall. X any metric space and A is subset of X, then A is complete metric space if and only if A is closed in X. Okay, now I will choose a Cauchy sequence in this metric space. Okay, this metric space. Okay, sorry. So let this sequence, be a Cauchy sequence in where A D sub. So S D sub S D sub implies, in fact, this is a Cauchy sequence in AN is Cauchy sequence in where, of course, here. D sub. But Bn, we know this is a complete metric space, it's complete. Implies An is An is convergent in Bn. Let's say An converges to A. So I need to show that this A as a sequence, in fact, this is something like this. Here I use the subscript and the superscript here. Is converges to 0, then it means this sequence, that guy, belongs to our metric space SD sub. Okay? That's the idea. I will show that this. Do you have any question?
No.
No, good. Okay, let me continue. So, must show, limit An is 0 in where, of course, this metric space, absolute. Okay, now let me start. Given epsilon greater than 0, so as An is Cauchy sequence, there exists M0 in N, this is something obvious, such that, this is a definition, for all M greater than M0, this depends N, M goes to infinity, not N, okay? M goes to infinity. D sub of An so Cauchy sequence means convergent. An, let's say Al less than or equal to, which is, let me say, sub An N minus An L N in N, N in N, less than or epsilon over 2. Okay? Let me, so don't use this. Okay. Why? Use the convergence, okay. So again, this statement is okay for this. So now, but this sequences belongs to S. What that means, in fact, limit N goes to infinity for all N, N is 0. This time N goes to infinity. This implies, in fact, we have found an M0. This guy goes to 0. What does it mean? It means implies there exists K0 in N for all N greater than K0, such that as this guy goes to 0, less than epsilon over 2. we have determined these two things, first one and the second one. Now we will come to show that, in fact, an goes to 0. But how? So choose n0 as k0. Then, for all n greater than n0, an, what is this? This is, I can write like this. This is less than or equal to, directly I am using the triangle inequality of So from this, one more thing, but this is less than or equal to supremum of an minus an m0 n n. No, this is 2 plus an m0. Okay, so this is true that this is less than epsilon over 2. In fact, it is true for all m greater than m0, hence, in particle for m0. This is less than epsilon over 2 for all k m greater than or equal to k0, but k0 equals to n0, so hence this whole thing is less than epsilon. It means limit a sub n is 0. This is a D sup, we know. This is an absolute metric. Okay, by using the previous inequalities, we will have that inequality. That means limit an is 0 implies an, so a equals to an belongs to S implies S is complete, implies S is closed in Bn. Do you have any question? Okay, let me continue. Problem 2. Let this time our metric space be a discrete metric space. Metric space. Okay. Prove that a Cauchy sequence xn in X is equal to a constant after finite terms, a finite number of terms. I mean, we will show that this xn is eventually constant sequence, okay? Hence, prove that, this is the first part, let me continue the second part. Prove that a discrete metric space is complete. This means any Cauchy sequence is convergent, but any Cauchy sequence here is eventually constant sequence, but any eventually constant sequence convergent in any metric space. Okay, let me solve this question. Let Xn be a Cauchy sequence. Solution. Cauchy sequence in X implies epsilon equals to 1 over 2. Choose a special one, 1 over 2. In fact, it is true for all epsilon, but in particular, it is true for 1 over 2. There exists n0 in n such that the xn less than 1 over 2 for all n greater than or equal to n0. But this discrete metric, we have the xn is 0 for all n greater than or equal to n0. If and only if xn equals to xn or xn0 for all n greater than or equal to n0. I mean, this is something like this. x1, x0, x1, x0, x0, continue like this. So eventually constant sequence. Constant. Any Cauchy sequence in discrete metric space, eventually constant sequence. So the first part is all done clearly. So completeness. What about this? Let xn be Cauchy sequence. Sequence in xd implies xn is
Hocam,
yes.
bölmek istemem ama bunu biz derste yapmıştık zaten.
Okay, I am is over, already over, almost over. Let me finish. Okay. Eventually, constant for above n0. What is this n0 is here, okay? Given epsilon greater than 0, the xn n0, say x, eventually constant, say x equals to xn0. Again, this equals to 0 as an eventually constant sequence. This is less than epsilon implies xn goes to x n0 x. So xn is convergent, implies xd complete. Okay, we have already done in the class for this question. Let me pass to problem 3. Problem 3. What about this? Let xd be, again, it's a discrete metric space, B. Discrete metric space. Prove that every function is continuous if G y dx is continuous. Prove that for all y in y, there is delta greater than 0 with gz equals to gy for z satisfying this is a metric in this is our topological metric space y, okay, less than delta. Did you solve this question in the class? Huh?
Ben hatırlamıyorum hocam. Yani
Okay, let me
çözmedik gibi.
okay. So what can I do? So I know X is metric space. I mean discrete metric space. At one point set is here open, but how? Let solution. U be open in Y. I need to show F inverse U is open in X. Must show F inverse U open in X. But how? How? So we can write F inverse U as a union of X in F inverse U X. Isn't it? Yes. But our X is discrete metric space. Ball X1. Then here only X can be in this ball. Because if the XY is less than 1, SD is a discrete metric space, X is Y by definition. But this is an open. Union of arbitrary open set is open. We have open. Implies F is continuous function. Okay. Let me pass the second part. Assume now our G1, G, X is continuous. This is given. In the question described in the property, we will show it, okay? So, but how? So, given y in y, I need to find a ball around y first. Let gy be x, okay? Then as g is continuous function, and this is the open set in X, this, I mean, okay? We have what? We have ball X1, sorry. First, start like this, equals to ball X1, open. So this guy is open as G is a continuous function. But this set is what? You know, it's a Z in U, GZ is X, if it's a GY. Okay. Since our U is open and Y in U, there exists delta greater than 0 such that X in, Y. Our Y is belong to this ball, clearly, and subset of U. So by definition, this ball is what? For all Z in. ball y delta implies z in u implies gz equals to x sorry, this is metric with implies. So last statement gz equals to gy with rho yz is less than delta. Okay, do you have any question? No? Let me repeat it, but here. One point set is open in X as a discrete metric space and G is continuous. I have that guy is open in Y. Okay. So Z in U, GZ equals to X equals to GY, this set, that guy. Since U is open and Y in U, X is delta greater than 0 such that this is true for all open sets U and subset of U. So let me pass this line. For all z in this ball means under this row. So yz is less than delta. Z in U implies gz equals to gy, so we conclude the property. Okay? Do you have any question? No. Let me pass the new question. Problem 4. What is it? Let, this is something obvious. Let our f x to r where x is a some metric space. Okay. Be continuous, this function be continuous. Prove that f a is 0 for all a in A prove that, let's if then fb is 0 for all b in a closure. So it means the function f on a closure are determined by subset A, okay? This A. So, but how? Since there's a solution, did you solve this question in the class? No. Since B is in a closure, there exists sequence extend so an in A such that an limit an is B. But f is continuous implies limit fan is fb. Is a sequential continuity. I'm using the sequential continuity, but that guy is 0 implies. Isn't it? And R is a complete metric space here. FB is 0. Do you have any question? No?
Hocam ben şey soracaktım ya.
Evet.
Bu soruyla ilgili değil, bunu anladım da.
Okay.
Bu Quizlerle ilgili bir soruya itiraz etmem gerekiyor da yani yazılı bir itiraz edebileceğim bir şey değildi. Hani onun için ekstra bir zaman ayıracak mısınız?
Okay, write down your objection write down it and scan it and make PDF, send me as an email, I will check it.
Tamamdır hocam. Ya biraz mevzusunu kullandım yani. Bu mevzu da kafamı çok karıştırdı aslında hani. Bilmiyorum, bir yandan Tosun Terzioğlu'nun kitabında var ama bazı sorular için tutmuyor ama Yıldıray Hoca da kullandı böyle. O soruyu da aslında sormak istiyorum bir yandan.
In the PDF you will be concrete,
Yo yo
so understand everything. Okay?
quizin haricinde hani sormak istediğim bir soru.
It's not a quiz, not related.
Aynen. Ya hem quizle ilgili var da quizin haricinde de işte birkaç haftadır sormak istediğim bir soru vardı. Yapamam
Okay,
diyor.
write down them and send me as an email.
Hemen o mevzusunu sorayım söz olarak. Hocam hani biz bir şeye convergent dediğimiz zaman bir sequence'a
Yes.
mesela mevzusu oluyor. İşte bir tane n0 bulabilirim ki diyorum. Sequence onu geçtikten sonraki term işte bir yere yapıyor. Küçüktür epsilon alıyor. Mesela limit x'en x'e converge ediyorsa işte bir tane n0 bulabiliyorum. X'en eksi x küçüktür
Yes,
epsilon
I understand.
Şimdi bu mevzuya göre şöyle bir şey var. Mesela ben x'en 0'nun da o zaman x arasındaki mesafesinin epsilondan küçük olduğunu söyleyebilirim. Çünkü n0 da n0'dan büyük eşit.
Of course.
Şimdi rastgele bir tane x'en aldım. X'en 0 ile arasındaki mesafeye bakacağım. Oradan geçiş yapabiliyorum hani. Triangle inequality yapmak için x ekleyip çıkartabiliyorum. Aynen. X ekleyip çıkartıp oradan getirebiliyorum. X'en eksi x artı yani mutlak x'en eksi x mutlağı kapattım artı işte x eksi x'en 0 yaptım. En başta da bunların arasındaki epsilon bölü 2 demiş olursam
Like 2 epsilon, you may say 2 epsilon, not so epsilon,
yani
less than epsilon, less plus epsilon, it means 2 epsilon, but our epsilon is arbitrary positive number.
aynen.
And you make it arbitrarily small, so 2 epsilon is okay.
Yani x'en eksi x'en 0 arasındaki mesafe epsilondan küçük gelmiş oldu.
Yeah, okay.
Şimdi mesela bunu eşit deme imkanım var mı? Çünkü for all epsilon için dedim. Ve epsilon arbitrary.
But for all epsilon, first you choose the n0. N0 depends on epsilon. For each epsilon, you choose n0. N0 fixed for that epsilon, not for every epsilon. N0 changes. As epsilon changes, N0 changes. If our sequence is, for example, eventually constant sequence, after some terms, so N0 will be fixed for all epsilon. But it depends. For example, 1 over n. 1 over n is converges to 0. For example, choose epsilon is 1. You choose the n0. Epsilon is, so n0 is here is 1. If you choose 1 over 2 the epsilon, n0 becomes 2. If you choose 1 over 2 as epsilon, it means your n0 becomes 3. Also, you may choose n0 is 4. It's not so important, but n0 depends on epsilon. Okay?
Anladım hocam.
Is it possible you may choose for all epsilon some fixed n0, but in general it's not correct.
Yani her epsilon için eğer ortak bir n0 bulabilirsem o zaman diyebilirim. Ama tamam.
It depends.
Anladım hocam. Teşekkürler.
Okay. So this problem is over. It is a problem 4 or problem 5. Let again f a function. Prove each of the following. knowledge. The part A is this. F is continuous if and only if FA closure is subset of FA closure of FA for all subset of X. Okay. I need to prove the two sides. First, I mean left-hand side implies right-hand side, then I will prove right-hand side implies left-hand side, so we are done. Okay, let me start. Solution. So, assume F is continuous, so we prove this part. Assume F is continuous. It means inverse image of any closed set is closed, isn't it? I will use it. Implies F inverse F A closure is closed subset of X. Subset of, yes, X. So, you know, A is subset of, but this is closed. Subset of what? F inverse FA. This is subset of F inverse FA closure is closed. Now, as FA subset of FA closure, it means we have this inclusion. Okay, that inclusion. So A closure belongs to F inverse FA closure and no closure. But as a closed subset, this is equals to that guy. So, last thing, okay. FA closure is subset of F inverse FA closure. This is subset of what? FA closure. So I take the first inverse image, then I push forward in the Y. So, but inverse image of FA closure, it means this set, that set belongs to included in this set. Okay, so we are done. So it means if F is continuous, we have this inclusion for any subset A of X. Okay, let me continue. So the first part is okay. What about this implication? Assume for all A subset of X, FA closure is subset of FA closure. We'll use sequentially continuity. It means I will let Xn be sequence in where X such that limit Xn is X. Okay? Is a small x. So I will show that, must show. Xn goes to F x. Yeah. Assume contrary. Does not converge to fx. So that means what? There exists epsilon 0 greater than 0 such that for all n in n, there exists kn greater than of n, kn, sorry, kn such that for all kn greater than, if there exists, let's say, kn is greater than n with, let's say this is a metric in y, fx greater than epsilon 0. Okay. Up to here, do you have any question? No. Define a subset of x. Sorry, this is a kn, xkn, n in n. Clearly, limit xkn equals as xkn subsequence of xn. So clearly A closure is what? A union X. But FA closure, which is F A union X, which is set Kn n in n such that when the union Fx is subset of FA closure. This is a property given in the question, property given in question. I'm using it. At the end, I will get a contradiction. So this means what? Implies fx belongs to FA closure. Implies there exists EM in F A such that EM goes to Fx. Here, let me explain. EM is xkn for some n, isn't it? I mean, xkn sequence has a subsequence which convergent fx, but this is not correct. Given epsilon equals to epsilon 0, determined above, rho f, so sorry, ym fx equals to rho xkn f xkn, sorry, this is the f xkn f. Do you have any question? Fx, but this is greater than for all kn. This is a contradiction. And E sub m cannot converge to fx. Implies, last lines, let me write the last lines. Implies, in fact, fxn converges to fx. So f is continuous. By sequential continuity, f is continuous, isn't it? So part B is this. Part B, again, f is continuous, if and only if f inverse interior A subset of interior f inverse A for all A subset of X. Okay? Again, we have two sides. Assume our f is continuous. No, this is given. So f inverse interior A is the open set is open in X. So implies interior f inverse interior A interior A. As an open set, we have this equality. So I need to show what? This is subset of f inverse A. Okay. Let me reverse it. F inverse interior A is interior A is subset of interior F inverse A as interior A subset of A. So we are done. Okay. What about this part? Assume for all A in X, not A in X, A must be in Y, isn't it? Let me change it here. Okay, correct. This is not X, in fact it is Y, not X. Hence, this is Y. Yeah. So we have that guy, F inverse interior A, subset of interior F inverse A. We will show that F is continuous. Okay, how? Let I0 open. I need to show F inverse A is open. Then interior A is equals to A. F inverse A is F inverse interior A, which is subset of interior F inverse A. This is subset of F inverse A. So I fuse this between the same thing, okay, F inverse A implies F inverse A equals to interior F inverse A. So F inverse A is open. Hence, F is continuous. Do you have any question? Here you may use idea. Which idea? So this means F inverse interior A for all A. And look like say another solution for all A in X. In fact, this is true for interior A complement. A complement. But this is equals to F inverse exterior A. This is, what is this? F inverse this is A. Okay, this means what? This implies, in fact, for all A in Y, sorry, it's Y, boundary of F inverse boundary A contains boundary F inverse A. Please use sequential continuity. Okay, so you will show that in fact F is a continuous. Problem 6. If the functions fxy and gyz both continuous, then their composition is also continuous. Is also continuous. Here, let U Z open. As G is continuous, we have G inverse U is open in Y. As F is continuous, we have F inverse G inverse U open in X. But G composition F inverse U is G inverse composition F inverse U, which is G inverse F inverse U open, implies sorry, this is wrong, huh? Isn't it? F inverse G inverse F G. G composition F is continuous. Sorry. Oh. G of his composition F is continuous. Problem 7. Do you have any question up to here? Let F and G be continuously valid functions real valued functions on X, prove that the functions f plus g, f times g, and alpha f are also continuous. This alpha in R. Here alpha is some real number. Okay, I think continuous. These two things are obvious. Show it. But let me pass the FG are continuous. How? Must show given x0 in X, f times g is continuous at x0. But our f and g are continuous at x0. That means implies given epsilon greater than 0. There exists delta 1 greater than 0. There exists delta 2 greater than 0. Fx f x0 is first clear. Okay. First, clearly, as any natural numbers is unbounded sequence, there exists ne0 in ne such that epsilon over ne0 is less than 1. Second, as f is continuous at x0, there exists delta 1 greater than 0 such that fx minus fx0 less than, this is important, epsilon of gx0 plus 1 times 1 over 2 whenever 1 over 3, whenever the delta 1. Third, as g is continuous at x0, there exists delta 2 greater than 0 such that gx minus gx0 less than epsilon over O and 0 times parenthesis absolute plus 1 times 1 over 3. Okay. Now I will choose epsilon for given, choose delta for given epsilon. Choose. The last thing is this. Delta S minimum delta 1, delta 2. Then observe that f times g of x. This is fx times g of x. Huh? Let's write fx g of x minus fx0 times g of x0. This is equals to, I will add something and subtract something. So we will get minus fx0 times g of x plus fx0 times g of x minus fx0 times g of x0. This is less than or equal to, so take the g of x parentheses, times absolute gx plus g of x minus g of x0 times fx0 absolute. So this is so we have one more thing. Times g of x0 plus last thing is this. Okay. So I know this guy is less than what? Less than, sorry, this is less than epsilon over g of x0 plus hope absolute 1 over 3 times, this is less than what? Epsilon n0 times fx0 plus 1 times 1 over 3 plus again this guy g of x0 absolute plus 1 times 1 over 3 yes, one more thing. Epsilon over n0 by g of x0 plus 1 up 1 over 3. So this is fx0. Okay. This is long but straightforward. Okay, come to here. Oh, I forgot here. I forgot. And now. Okay, now it's okay. So this is less than 1. Whole thing is less than 1 as the numerator greater than, so this guy greater than 1. So this is less than 1. This is less than epsilon over 3. Whole things is less than epsilon over 3 as numerator greater than 1. So this is less than epsilon. So we have epsilon over 3 from first one. Again, this guy is less than 1, so it's less than epsilon over 3. So now, sorry. This is less than 1, so n0 is greater than 1, so this is less than epsilon over 3, which is epsilon, implies fg is continuous at x0, but arbitrary. implies our FG in fact is continuous on X. Do you have any question? Let me solve some problems about Cartesian product of metric space. In fact, maybe problem 8, I don't remember. So we have 20 minutes. Let X be product of two metric space. Prove that a function fy to x is continuous if and only if fy equals to pi. These are projection maps, projections. F y to xi continuous, I equals to 1 over 2, continuous. Okay, they are projection maps. Now I will use the sequential continuity use. Let me pass the new page. First, observe. Let En be sequence in y with limit yn is y. Then Fyn is sequence in is metric spaces, product metric spaces, and Fyn implies this equals to x1n, x2n, and this equals to x1, x2. We can write this like P1 composition F xn, sorry, yn, P2 composition, let me, yn, F yn, and similarly P1 composition Fy, P2 composition Fy. Okay, now assume F is continuous first. After this, the last things, this is F1 yn, this is F2 yn. This is F1y, this is F2y. Okay. Now, prove the implications. Assume F is continuous. Then, as yn converges to y implies Fyn converges to Fy. So, x1 and x2n converges to F. So, low 3. x1, x2. I mean, given epsilon greater than 0, there exists n0 in n such that, so this is a, take the absolute maximum of the matrix D1, D2, respectively, they are matrix on x1 and x2. of less than epsilon. But we know rho, d1, x1 and x1 less than rho infinity and d2, x2 and x2 less than rho infinity less than epsilon less than epsilon. So for that epsilon, choose above n0, and for all n greater than equal to n0, we have di xi and xi less than epsilon implies xi and goes to xi. But what is the xi here? But xi is f, sorry, I will not write like this. Xi is what? Yes. F1, so fxi yn xin converts to xi, which is fi y. So implies fi is continuous. For I is 1 and 2. Okay. The other part, what is this? Assume f1 and f2 are continuous. So we know that fi yn conversion to, say, xi. Okay? So for second part to xin, so this is xin conversion to here. So implies, let me pass the new page. Implies what? Given epsilon greater than 0, there exists, so ne1, ne2, it means there exists ne0 in n such that I take the maximum. For all n greater than n0, di xi and xi less than epsilon implies maximum. Sorry, rho x1 and x2 and of x1, x2 as a maximum of di's as maximum of di's xi and xi 1, 2, but all less than epsilon, this is less than epsilon, implies x1, so fyn, which is x1 and x2n, goes to x1, x2, which is fy, implies f is continuous. So we are done. Do you have any question? No. The other problem, problem 9. Problem 9. Let E be E1 cross E2 and PI's donate projection. PI. Here, prove that, what is the question? Prove that A subset of E is bounded if and only if PIA in AEI is bounded. Okay, what can I do? First, observe that we can write A is like P1A cross P2A. You may observe it as taking an arbitrary xy in A, then take the projection, then xy belongs to that set. Okay? So A is bounded. A is subset of this ball. I am using the raw infinity ball. Some x1, x2 in our set E. For some epsilon greater than 0 and in E. If and only if P1A cross P2A subset of ball infinity x1, x2 epsilon. If and only if P1A, we know that D1 x, so B1 x1 epsilon cross B2 x2 epsilon subset of this guy cross, sorry, not cross, sorry, up, subset of B1 x1 epsilon. This is a ball with respect to metric D1 and P2A subset of B2 x2 epsilon. If and only if both P1A and P2A is bounded subsets. These are of E1 and E2 respectively. Okay? Do you have any question? So we have more or less 7 minutes to solve another question. Problem? Question marks, let's say. I don't remember. Let X some function on the closed interval, closed finite interval, real valued function, be a continuous real valued function, and for 0 less than s less than 1, define new function, our new function, that is phi x s as integral 0 to s, it's dt. Okay. Prove that this function 0, 1 to r, real valued function on this closed, finite closed interval, is continuous And also this function from this set, continuous function on 0, 1 to itself is uniformly continuous. So, solution. Given x0 in 0, 1, I will show that this phi x continues at that x0. So x0 is arbitrary point. In fact, it's continuous on whole closed interval. Observe. Our phi x s minus phi x s0, which is integral 0 to s xt dt minus integral 0 to s0 xt dt. This is equals to 0 to s what xt dt. This is okay. As x is continuous function on finite closed interval, finite closed interval, there exists m greater than 0, such that here this must be S0. Okay? S0. Such that there exists such that xt less than n. Now, given epsilon greater than 0, choose our delta as this number. Then, if s minus s0 less than epsilon m over 4, then this guy is, as you observe above, xt dt. But this is less than or equal to up. So this is less than or equal to which is this is less than n okay, that guy is n. This is less than epsilon, implies this function is continuous on 0, 1. What about the uniform convergency? Now, given x, y in our set, the continuous functions on finite closed interval 0, 1. Observe that here metric is a sup metric, d sup x phi x phi y equals to supremum phi x s phi y s here s in this closed interval. What is this? This is supremum. If you write the integrals of 0 to s xt minus yt dt. This is less than or equal to supremum zero to s, one more absolute dt. But this is less than or equal to supremum 0 to s dt, s in here, times supremum xt minus yt. This factor, this time s becomes t. Clearly, that guy is 1. And this guy equals to d infinity xy. So let me conclude the statement. So for given epsilon greater than 0, choose delta is epsilon. Whenever the infinity is sup or infinity xy is less than epsilon, the infinity as observed in above less than epsilon implies phi on this set is uniformly continuous. Okay. Do you have any question? No. Okay, this is stop the share. This is end of our third recitation. Okay.